first thing is to just get G11. Are there issues with getting G11? Anyone having a problem getting G11? It's just E minus epsilon minus, what did we say? Minus, or what's our self-energy? It's E minus, I guess we wrote it down last time. It's going to be E minus epsilon. Oh, thank you. E minus epsilon, I guess. Is this the way we write it? Minus 2 magnitude T e to the I Ka inverse. And isn't that going to be G11? Because now your device is just one node, and so you just fold in both the left and the right self-energies. They add together to become 2 T e to the I Ka. Is my sign right in front of the
No.
Is it plus?
Yeah.
Is it plus? Okay, so that's that. And then, you know, and I ask you to write it in terms of these various, and as we said last time, I finally did get the video from last time posted, like yesterday, I think. Took a while. It is posted. It's linked on iLearned also.
It's still not there.
It's not there. Where? Oh, no, it's under assignments. It wasn't a lecture. It was, so I put it under assignments.
Oh, I see.
And so, you know, as we said last time, once you get this, then you just use those relationships between that we get from our dispersion to relate this expression to K and velocity. You're already, I mean, you got to relate K to energy. So, right, we have E is equal to epsilon. Is it in terms of the magnitude of T? Is it plus 2?
Minus
I
magnitude.
can never remember. Minus
Magnitude.
2. Thank you. Minus, is it 2 magnitude of T? Yes. Cosine Ka. Right, which is minus 2 magnitude of T. 2 cosine Ka is, okay, I'll get rid of the 2, e to the I Ka plus e to the minus I Ka, and I get rid of the 2. So you use those relationships to so, you know, change between K and energy, and also you use the velocity as 1 over h bar dE dk, which is just going to give you, 1 over h bar times, what, 2t magnitude t sine Ka times a, I guess, right? It's going to be 2t a. Right, I guess that's velocity. So you play around with those relationships to write it in these different forms as a function of K, velocity, and energy. And then, well, then you just, this is a scalar, so you're just taking -2 imaginary of the G11 that you just calculated, and you've already got it written in terms of K, V, and E, so you just write your spectral function in terms of K, V, and E. And I guess I can't, yeah, I can't even remember the form of the density of states for this tight binding dispersion, but I assume we did it last quarter in 208, should be in the notes. So you just show that number 3 is true using the density of states that we calculated last quarter for your tight binding dispersion. I don't know if we went back, did we actually go through, did I actually do the calculation d of e is, what is it,
You mean this equation?
1 over L sum delta, oh sorry, delta E minus E of K. Did I explicitly do that? I can't remember.
Yes.
I see.
For
For that tight binding chain.
Yes.
Yeah, I see. Sum over K. So that's in the 208 notes. All right.
can I show you?
Yeah.
The notes is already in front of me.
I see.
So this was the main equation.
Right.
So I'm going to use this for converting to integral.
Yeah.
And for that, so this should be my equation. This is the equal relationship I'm
Yeah.
using here, and just calculate the integral.
Yeah. Yeah, because yeah. It's got to be an easier way of doing this. He always did it in a very simple way, calculating the density of states.
Yeah.
I can't remember what I mean, he's actually going through this, converting this to an integral and all that, which is kind of painful. I can't remember, what did you do? It would be good for like the other students to show your way, since it's so much simpler. I'm trying to remember what you did. You would just calculate n as a function of
So for two-dimensional, it was easier. Like you just go through. It is
Area
It
inside
is
the
the area
well,
inside
for
the
1D it
circle.
should be.
So
It's just
it
the
should
length,
be
right?
just length.
So what? Let's see. You would calculate n. You would calculate like n as a function of e or something,
Yeah, it is the density of states, right?
and then you take the derivative to get the density of states.
I calculate the total number of states inside some isosurface, and then just took a derivative. That is my density of states.
I see. So you in terms of our a 1D Brillouin zone, you're saying, so this is 0, pi over a, and minus pi over a. Do you calculate first like n of a given, I'll call it this K Fermi, like n of Kf?
Yeah.
Which in this case is very trivial, right? I mean, Kf is a plus and minus Kf. So it's just going to be, we got to convert that. 2K, it's the distance, the total distance, 2Kf, divided by the number of K states there, which is the delta K is 2 pi over L. So I guess 2Kf over
2 pi over L should be.
over delta K, right?
Yeah.
That'll be the total number of states.
Yeah, I have to just convert this K into energy and take a derivative. That
Which is just Kf over pi, right? Kf over pi times L, but we're gonna do it per unit length, right? And then you just get rid of the L if you do it per unit length. This is 1D. And so Kf, so then you got to convert that to energy using your dispersion relationship, right? So.
But that was like for parabolic. In this case, it might.
No, this is true for any, right? Now,
Yeah, that is
now
true,
we
but
make this relationship that E is epsilon plus or minus 2t, minus 2 magnitude t cosine KFA. So now I want to do dNdE, right? Is what you need? dNdE?
Yeah.
Okay, so that's dN dk dE, right? And so that's 1 over pi times oh, I guess I better do dE dk inverse. 1 over pi times. I don't know. I can't, does anyone, I can't remember the derivative of the arc cosine, so I guess I better do. So dE dk, what's d? Oh, that's my velocity. Oh, so dE, oh, this is like dE dk is equal to h bar times velocity, right?
Yeah.
And so dE dk inverse is 1 over that. So that's 1 over pi h bar times velocity. There's the density of states in terms of velocity. I did the easy one. I'll leave you the hard ones for energy. Y'all see that?
Why you have an alpha here?
What's that?
Why you have alpha?
So this was for non-parabolicity.
Yeah, that's when we
Structure.
that's when we did it for very small k, and then you can approximate it as just this. You expand the cosine out to just second order, and you keep only that, and you get it into this other form. And that's only good for just small ka. Near
I
k,
see,
near
yeah,
k,
I remember.
near the band edge. Okay, well I did the one for velocity. I did as usual. I do the easy one for the hard ones. But I mean, once you have it in terms, I mean, the velocity is like sine, and yeah, then it's kind of just manipulating the sine and cosine. It becomes geometry, really. Okay, other questions?
So would you just like go through the 5? I mean,
Oh, 5, yeah. But I mean, I guess we have the exact expression in the 208 notes, hopefully. So I gave you one for velocity here for density of states. So in the 208 notes, hopefully, do we have the exact expression for the density of states for the cosine band? Or
I
did
don't
I?
think so. But there is, for two-band model, there is an exact expression.
But I didn't do it just for the single type binding band?
Let's see it.
Okay, so, I mean, once you have it in terms of velocity, what else can we do? dE dk. So, dE dk is 2 magnitude of t of 2ta sine ka, and I mean, we have the 208 note. Oh, the 208 notes are on iLearn.
I have it.
Oh, you have them open, but you
Yes.
don't see anything. No, I mean the actual PDF of my 208 notes. So I did it for the 2-band model.
PDF.
What's that?
I was looking through last night and I saw the form of the
That's it. I didn't actually go through it. Well, once we have it in this form, it should be easy to go back and forth. So let's see. So dE dk is that. And so sine Ka, right, so that's my dE dk. I'm going to need the inverse of that eventually, but I just want to solve for sine Ka in terms of energy. So I know that E minus epsilon over 2t is cosine Ka, right? And so, and then it just becomes geometry. So if this is cosine Ka, E minus epsilon over 2t, this is 1, this is the square root of 1 minus this stuff squared, 1 minus E minus epsilon over 2t quantity squared. Right, that's sine Ka, right? So I get dE dk is 2ta times the square root of 1 minus all this stuff squared, E minus epsilon quantity squared over 4t squared. And I multiply through, I guess, 2t inside, and so that's equal to a times square root of 4t squared minus E minus epsilon quantity squared. I don't know if one form is better than the other. That should be sine Ka. Well, I mean, that's dE dk. And then I need the inverse, right? The inverse is what we needed to get the dN dE, the density of states. So it's 1 over pi times the inverse of this dE dk. 1 over pi, so the density of states is 1 over pi a times the invert times 1 over this square root 4t squared E minus epsilon. So you've already calculated G11. I have no idea. This doesn't look like G11 to me, but you can check it, right? You've already calculated G11. Does it look anything like this? Oh, good. Excellent. That's reassuring. So this would be in terms of energy. And so we did velocity, we did energy. The only other thing is K, which you just leave it in terms of, what do you need? And it's already in terms of K, I think, right? dE dk is in terms of K, so it's all, I mean, you naturally get it in terms of K. You just have sine Ka instead of velocity, right?
Yeah, what is the underlying physical reason that my spectral function has to be some constant multiplied by density of state?
Your spectral function is okay. Physics. We wrote it in a number of different ways, but the way I like to think about it is the spectral function was equal to this electron function plus this whole function. And this is just, the number of occupied states, and this is the number of empty states. And if you add them together, that's the total number of states, which had better be that's what your density of states is. It's the total number of states. It doesn't care about occupation. And it turned out to also be related to, GR and GR dagger. But this is the most physical way I like to think about it. It's the sum of the empty states plus the occupied states. It's the total number of states.
And how can I predict the constant that I have to multiply by
To get
density of state?
so this is the total. This A11 gives you. Well, let's see. I mean, if I integrate A11, I think this is a final problem. If I do this integral, integral dE over 2 pi A11 of E, because we only have, our basis is one orbital per site, then we said show that this is equal to 1. And this is basically telling you, the total number of states on each site is 1. That's telling you there's one orbital per site. And for the density of states, I need to integrate, dE, d of E, and this should give you the number of states per unit length in this case, right? The number of states per unit length is just one orbital per lattice constant, right? And so you just kind of match those two integrals together. Right? The number of states per unit length is one orbital per lattice constant. And so and that's where you get the 2 pi over A, right? The relationship between A and the density of states is this factor of 2 pi over A, or A times, how do I do this? The spectral function divided by 2 pi A is the density of states. That's it. Right? So A11 over 2 pi A is D. And so I guess if this is the density of states, I guess the last problem is showing that the integral of this, or within some factor of 2 pi or something, or 2 pi A or whatever, gives you 1.
So since my bandwidth is, I guess it is 4 here, since we are considering cosine band, so the integration limit should be from 0 to 40. Is it
Yeah, I
correct?
mean, I just set epsilon equal to 0 here, and then you integrate from, I guess, minus 2t to plus 2t.
Okay.
Right? Minus 2 magnitude of t plus 2 magnitude of t. But it's symmetric, so you integrate from 0 to 2t and multiply by 2. And I was just looking back. There was some sneaky trick I used in the solution because I hate doing math, but I love sneaky tricks. But if you look at the definition of the density of states, right, the integral you're doing is this. That's the integral you're doing. Which means you just right? That's the integral of dn. And I think there was in dE, what is dE? dE is so if I wanted to change variables, right, instead of integrating over energy, this integral is also the integral of dk dE dk times my density of states, and my density of states is dE dk inverse dE dk inverse dE dk inverse, and this was just 1 over pi, right? This thing was just 1 over pi. So dk times 1 over pi. And I integrate k over all k from minus pi over a to pi over a. Well, now that's an easy integral to do. And what am I going to get? I'm going to get 2 pi, 2 pi over a divided by pi, so that's 2 over a, and you got an extra factor of 2 somewhere. Oh no, when I do it this way, this is just the magnitude of k, right? K is just the magnitude of k, I think. I don't know, you got to be careful here. You got to be very careful because it's the magnitude of k, well, I don't know. At any rate, if you're careful, you can do it this way too. And otherwise, I think this is related to, like, you know, an arctan or some arc cosine interval, which will give you 1. All right, so what else did you have to do? Is that it? Oh, and then show that, I guess number 5 we had to do also. Show the transmission is 1 for per ambient. So yeah, that was just, so you've got the exact green function G11. So it's just G11 magnitude squared times gamma squared. And show that that's 1. And gamma was, so you've got sigma, so, right? So the transmission, in this case, is G11 squared, gamma squared, and gamma is equal to, well, I guess first, sigma was 2t,
Should we switch to
yeah. So sigma was, so that's your transmission. Sigma is 2, again, is it E minus H minus 2 magnitude T e to the IKA? Is that the way it's written? That E minus H minus 2 magnitude T e to the IKA?
Plus.
Oh, plus 2. So then you got to, so sigma is defined with a negative sign there. Because it's defined as E minus H minus sigma. There's a minus there. And so gamma is, just like A is related to the green function, gamma is related to the self-energy, is negative 2 imaginary sigma. And so you've got gamma, you've already done G11, and that gives you your transmission, and you show us 1. I mean, you can already see what gamma is, right? This is going to be 2 T sine Ka, which is, you know, related to your velocity. And you know your green function is like 1 over velocity, so it's pretty clear you're going to cancel. I mean, it's exactly equal to velocity over A times h bar or something like that. Meters per second. Yeah, that's the right unit, so it must be V over A times h bar. But you're going to take the square of that. Oh yeah, you're right, because of a 2 and a 2. This is a 4. So this is must be a 2 out here. Twice the velocity. All right then, well then, no more questions? I say let's call it a weekend, or a week.
I have a question.
Okay.
Like, you explained something about the imaginary part of the self-energy, but how about the real part? How do you understand that one?
Well, the real part gives you a real shift in like the site energy in the simple model. I mean, it's just moving the site energy up and down. And we drew a picture of that. And, I mean, you need that there because we showed that if you just take this 3x3 effective Hamiltonian, it reproduces the exact energy spectrum of your infinite chain. And so you need that shift to get this full bandwidth of 4T. So at like, I can't remember how this works. At the lower edge of the band, it moves the site energy down. At the upper edge, it moves it up, and it captures the entire full bandwidth of 4T, which yeah, I don't know, but we'll talk. I think you'll see that it'll come back to you more on the next homework assignment, where we're going to do this model, this simple model for a resonant level. It's basically what you just did, except you use a simple approximation for the self-energy. You don't really calculate it. You use this effective self-energy. And the picture is like this, where you have a resonant level connected to the leads, but this connection is different from the and usually it's much weaker. So if these are like several EV, this is like maybe 1/10 of an EV or something like that. So you get a weakly coupled central site. And yeah, so the real part of the self energy, what I'm calling little sigma here, just gives you a real shift. And the imaginary part is the finite lifetime effect.
And for the lifetime, because like the way I see it is like when the electrons from the lead goes into the device, you will have generally some impulsion. So it's like
Say that again. You generate some what?
repulsion or impulsion.
Well, you're saying repulsion. I mean,
Repulsion.
no. I mean, we're not taking into that account really. The way I explained it was, if you just put an electron in the middle of your device, after some time it's going to disappear into the leads. And it's disappeared out of the device. That's probability density is gone from the device region. And that's the finite lifetime effect we're talking about.
You mean it should disappear in the device, right?
It leaves the device, it goes into the leads. Once it's left the device, it's gone, because we're only considering the device domain.
But it's because you mean so you mean it goes back to lead?
Yeah. Right? It has a velocity. You can think of it in this ideal where we arbitrarily, we had this ideal infinite chain. We took the central 3 sites and arbitrarily said this is our device. So every electron is in a K state, moving to the left or to the right. It's only going to be in the device region for a very short time. Then it's gone. And so these imaginary part of the self-energy accounts for that effect, this finite lifetime effect. And the same reason when you have a resonant state like this, you can have a very sharp resonance, but the width of that resonance is due to the finite lifetime. Every resonance has this Lorentzian-shaped peak, like an optical cavity, like a Q factor, right? And that's due to a finite lifetime effect. It's just like the Q factor from your RLC circuit, or in an optical laser cavity, like roughly the number of times it goes back and forth before it goes out, leaves the cavity. That's the finite lifetime effect in a system like this, where it's weakly coupled, and it will, like, in a finite length region, it would bounce back and forth multiple times before it would escape to the left or to the right.
And because like for the relation between the lifetime and the self-energy, it's not valid for incoherent, right?
No, even okay, it's a different self-energy. But there is a self-energy representing incoherent scattering events, which we have not talked about. But the imaginary part of that self-energy also represents a lifetime, that you are in a given K-state before you scatter and go to some other K-state.
But there's no relation between lifetime and self-energy anymore.
Yes, there is. It's the same relationship. Gamma equals -2 imaginary sigma. And gamma is h bar over tau. It's the same, exact same relationship. Really, truly, promise.